record, it will stay on. It will stay on all the time it's recording.
They're much better now, actually, the illumination.
Your gains are it's on a high gain, yeah. I wonder why it's hunting. I wonder why it's hunting on the focus. It's low light. It's low light.
Maybe I ought to put it on
manual. Yeah, I would think so. Because it's going to be fixed, isn't it?
It is really today. Let's see where the autofocus goes. Because this little viewfinder is not so good, it's difficult to tell. That makes it, yeah. I didn't know that existed.
There normally is a focus on there.
I think that was out of focus. That's better. You point the camera at something that is in a good light source, the person who's standing, and then put it into. Just move that way, and I'll put it into manual. I'll put it in manual now because I think that was actually that looks okay.
Okay, if I can get a lead, I'll drop it in during your lunch break, 1 to 2. Yeah, sorry, I thought they were all in the box. I thought it was all. It's not in there. I've looked. Well, not that I can find. I can't find it.
I'll leave it like this for the day, I think, because in this position, when I used to visit this I was quite often moving it around because the speaker was to the left or the right. In this central position, it's wider, I think, so I think he's going to stay in shot all the time, I hope, anyway.
That's a bit loud, that's better.
No, I think that's okay.
Okay.
Okay, thanks.
Can we just try and put that on the video mic? You want me to try? Yeah. And then you want to hear what I'm saying? Anything coming through? You want to keep talking? Yeah. Still good. Okay? Right. Now I'll go away.
Good morning. My name is Chris Fitzwell. I'm a member of the Committee of the Computer Conservation Society, and it's my great pleasure to welcome everybody here today to this seminar on the development of the 360. The timetable for the day is that we'll have 3 talks this morning. We'll break for lunch at 1 o'clock, have an hour's lunch break, and resume at 2 o'clock. And hopefully wind up with a summary at 4 o'clock and questions after that. We may also have time for questions at the end of the morning session. My contact with 360 was a relatively early one, and not as early as I imagine most of the people in the audience today. As a relatively young journalist, I went on a train down to Hursley one day in April 1964 for the UK launch of the 360. And I do remember that because one of the factors that day that sticks in my mind was that the managing director of IBM UK, Tom Hudson, travelled on the train with us. I thought that was a good bit of PR. But it was an interesting day, and little did I realise at that time that it was going to be the start of something which would probably, did occupy a great deal of my time as a journalist over the next 10 years or so, during which we launched the IBM 360 figured very largely in much of that coverage. I'd like to introduce then our first speaker, who will set the scene on the development of the 360. Peter Tippmann started his career with Leo in 1957, developing core memory systems for the Leo 2C and Leo 3. He joined IBM in 1960 and worked on the announcement planning of the System 360. He moved to IBM UK Hursley Labs and worked on a variety of projects, including PL1, LSI, array logic, graphics and text systems, and the PICS transaction processing system, which is happily still with us and doing well for IBM at the moment. He retired from IBM in 1986. Peter is going to talk about the background to the launch of the 360, the market environment into which it was launched, and we'll talk about the risk, particularly, of launching into a market with such an ambitious project, and he will also cover the programming element as well. Peter Tippmann.
Thank you, Chris. Yes, your program probably tells you that I was going to talk about the environment. Actually, I've got to slip in something else, because though it was actually not true of the 360, though people often claim it, after we'd gone through the talk, we discovered that we hadn't covered programming at all. So someone had to talk about it, and I was the only person who was remotely concerned with programming, so I got landed with the job of slipping it in as an extra. Now, the 360 wasn't like that, though some people think it might be. So first comes in two pieces, and this is the contents of the first bit. I hope if I press that something useful happens. The view of the market's a very personal view. The reason I got into this situation was when I joined IBM, I joined as what was called an applied science representative, which meant selling to universities and engineering installations, trying to sell them scientific machines. And that job disappeared almost simultaneously with the announcement of the 360, because it was realized we shouldn't have separate marketing organizations for the scientific market, commercial market. And since I got promoted to the point where I was in Wigmore Street in headquarters, and no one had anything to do with me, and there was this system coming up which wasn't going to be announced for 2 years. And from the salesman's point of view, something that's not going to be announced for 2 years doesn't exist. And I was a spare slot, so I got assigned to worrying about what was going to happen in 2 years' time when the 360 was announced. So I spent some time worrying about it. And therefore my view is quite different from the people you'll see later on today who were actually involved with delivering it. I was concerned with what had they got us into and what were we going to do about it. They were concerned with doing it. And it's quite a personal view. I've noticed that in other historical discussions of this organization, you'll hear as many people stand up and give an account. Each one is totally different. I mean, they contradict each other. They have quite different interpretations of facts as well as opinions. So anything I put up is just my view. Oops. Sorry about this. That light is quite dazzling. I can't see why now. Having said it's a personal view, the main source of the numbers on this is John Henry's book on Innovating for Failure, which is about the lack of success of the British computer industry. And it's very hard not to appear boastful with an IBM and standing up and saying, gosh, weren't we marvelous? I mean, the fact is, we had an enormously powerful marketing position. And we're talking about at the end of 1961, beginning of 62, when we were selling the 1401 in absolutely incredible numbers. The 1401 you could take to a company that had a punch card installation. If they had 2 accounting machines and a calculator, you could sell them a 1401 for the same price, and they would be doing far, far more with it. And they could do it simply. I mean, people in those days were doing really primitive things, most of them. I mean, just getting the invoices out and getting the money back was a chore that they were delighted to get to the machine. Getting the utility bills out, you know, just simple things. Inventory management, demand forecasting were really complex, way out things. Looking back to 61. Now, there were some people, of course, who were doing more complicated things, but they weren't in large numbers, and they weren't the revenue stream. The revenue stream was coming from really basic things. And we did have incredible control over the market in IBM. In talking in a worldwide sense. Of course, in the UK sense, we were strange in that we weren't the largest company. In almost every other country, we were. But looking at those numbers, the way we looked at the market, and in those days it was God-given, we just understood the market was like this. There were large machines, medium scientific machines, and there were commercial machines. That got us to 6 segments in the market. As far as development was concerned, world trade then had about a third of the volume that the US had. World trade being all the rest of the world except America. So we were trying to expand the market view into a 12-cell market view. So we had 6 world trade segments and 6 domestic segments. And looking at the top left one, where the volumes were real, that's the big revenue stream was coming from there, the top left, and as it happens, the bottom right. But I came from a Leo background, where we had to beg for every transistor, where I designed memories, and when I finished that, they said, right, now you can go and do the tape channels. You know, we were that short of people. And IBM had so much more resource. I mean, we sold, these were the numbers we'd sold by the end of 64. We'd sold 13,000 1401s, compared with, say, the RCA 301, which ICL also sold, and the ICL 1301. I mean, they were orders of magnitude different. And when that came to how much programming support you could provide, all the rest of it, it was just enormously large. So the first message is we were really strong. And as it happened, we were really strong in the top left and the bottom right. The large machines, even in the UK, we were dominant. We had good political reasons for being dominant, because the people who bought large machines in those days, the Atomic Energy Authority, or CEGB, related people like that. And politically, at that time, they were very closely tied to the US nuclear industry. So they had a very strong incentive to buy the same machines as were being used in the US. So that was one reason why we had 790s in Aldermaston and in CEGB, and other 704s dotted around in Risley, places like that. So we had a very strong presence there. The place we were weakest was the scientific, the small, and in the UK, the small scientific. I sold 1620s when I first came into IBM. 1620 was a lovely little desktop machine which had a memory of 20,000 decimal digits and a typewriter. And you really sat down and used it like a PC. But it cost more than an Elliott 803. It's code name. Pardon?
It's called Cadet.
That's right. It doesn't even try, it's called. Did arithmetic by table lookup. And it had the most unbelievable paper tape reader you can ever imagine, designed by someone who had designed magnetic tape readers. And everybody knows the way to sense timing on a paper tape reader is to sense the sprocket hole. For a bonus, it screwed up the socket holes as well. So we weren't well placed in that piece of the market. But in the US, we did sell it. We sold it to universities because we were IBM and universities bought machines. The 803 was much, much better. And they sold, almost uniquely among the UK machines, they sold a reasonable number. Abroad as well as at home. So that was one reason why John Fairclough got the job of having a small scientific machine developed at Herzog. And that began to raise a question. Because for companies like Esso, who could buy machines in any part of the world they chose to, but we chose only to maintain them in the countries we sold them. Esso were very unhappy that we didn't always immediately announce things in the UK that we had announced in the States, because their parent company wanted to have the same machines as the subsidiaries Esso had done. But at the time, and it was only in hindsight that I would recognize this, were not that good, because it raised the question of how, if we had something brilliant announced in world trade, we were not going to announce it immediately in the States. And that was one of the issues that brought the whole thing to a crunch. Should we have a separate UK product line? Or rather not UK, but a world trade product line. Don't forget, in those days, the disparity in wealth between the States and here was much greater. An American cost about twice as much as a European, as an Englishman, and about 3 times as much as an Italian. In those days, we cost more than Italians. That was a fairly big discrepancy. So when you came to do sums about displacing people and so on, you could bear much higher costs in the States. So there was a reason for thinking that the world trade market was different. Therefore, but the big decision was it wasn't different. So the only real point I'm making is, I'm only going to just leave that chart up there for you to look at and point out the huge difference in numbers. We had a very, very strong position. And anybody in such a strong position, you would think, would normally say, well, let's keep on doing what we've done. That's jolly successful. And it was absolutely remarkable that IBM decided to do something different. You know, if we were doing so well, why change? Apart from the market, the other thing that we had enormous strength in was technology. People in this country, certainly, you know, I saw it from Leo, but we didn't understand the strength of depth of technology that IBM had. As I said, when I finished doing memories of Leo, I was put on to looking at tapes. And we looked at the Decca tape had not been a great success on Leo 2. EMI were trying to make tape drives, but the main people you looked at were Potter and Ampex. And Leo in 3 actually went for Ampex again in another writer. But we had no conception of actually being able to do anything like make our own tape drive. But IBM tape drives, I had thought at the time, were terrible, because they used to do dreadful things to the tape. And they had pitch roll capstans that used to grind it, and it ran over in contact with the head, and they needed quite a lot of maintenance.
The high performance rate was called euros.
And what I didn't realize, and it was quite obvious, if you wanted to get faster tape, which everybody did, you could either make the tape move faster or pack more densely. If you pack more densely, it was a huge advantage to have your head in contact. But no one else did. Everybody else ran out of contact because they felt that they couldn't manage the wear on the tape. Only IBM had the resources to say, well, if that's a problem, we'll solve it. And they solved it by developing their own tape, heavy-duty tape. And they had the technology right through, from the materials technology, the tape technology, the drive technology, the controllers, everything. And no one else in the world could put that lot together to make a new solution. And that's not on that chart. In printers, we had the most amazing. The 1401 printer was a really new idea. When everybody else had analog drum printers, a great big drum went round and round, and you had to bang it at the right time. If you didn't bang it at the right time, the letters went up and down a bit. The IBM answers had this chain which went round this way, and you had to bang it at the right time. If it was slightly out, the letters went up and down, they were slightly left and right. And that didn't look nearly so bad. Surprisingly, psychologically, it looks quite different. A letter slightly to the left is quite different from a letter which is out of line, up and down. And it's cheaper. You just had this one chain. And the chain itself is replaceable, so you can have different fonts. And you can have upper and lower case, and all those sorts of things which were unthinkable on the old landlines. So, I can remember the Power Samus printer on the Leo 2. When Power Samus really didn't believe in electricity. If it was down with the bone cable, it was down with the bone cable. Electricity was over dangerously you find this was a totally different machine in terms of simplicity, reliability, all the rest of it. So that they were there. Discs, the first disc paper I could trace is from around 1953, when there was a theoretical study of floating ahead on a disc. So the air-bearing disc. And the 305 Ramac was not a success. Not really. It had 5 megabytes of memory, and the arm went up, in and out, up, down, like that. It was a single arm, moved around, access time in order of seconds. But we were learning about that, and by the time we got to the 360, we had not only realized that disks were very important things and far better than tape, but it was an enormous advantage to have your operating system on the disk. Because if operating systems on tape were continually churning up and down, you've done a compile, then you want to do some link edit or something, you have to get another piece of tape or another tape drive or somewhere else. There's a lot of movement trying to get the flow of jobs through a tape machine. So we were onto disks. We were almost a monopoly on disk technology. I can remember John Binkton coming into the floor of Wigmore Street. It's not here. To look at buying IBM disks from us, because there wasn't anybody else to buy from. So Leo had to bought disks from us and resell them on to their customers at some other extortionate rate. Tremendous disadvantage. And of course, a lot of other people just didn't go into disks at all. But we definitely had a disk technology that was good, reliable, and we understood about disk operating systems. The other thing was memory. I mean, memory was just amazing. I mean, we had invested a lot of money. And the reason we were ahead was not because we were just big, but we invested a lot. We invested a lot in a plant which automated the process of making a memory stack. And it automated everything, including the read wire. That goes zigzag through the plane. And they took these planes and stuck them together mechanically, but automatically. The whole process was automated. And we could sell memory for about 5 times its manufacturing cost. About more than that. When the manufacturing cost of memory was nothing. We just made enormous profits on memory. On core memory. So, we had, again, I'm just laboring the point, we had immense strength. And yet, we were onto this very risky venture. Why on earth do we have to tear up our existing set and produce a new, totally incompatible range of machines? Well, the spread report doesn't make a big deal of it, but I was conscious at the time that customers, people like ICI, were going around and saying, we really would like to have the same machines in all our offices, all our computing centers. They were looking for standards. As far as IBM was concerned, we were having to train customer engineers, train support engineers in all sorts of different machines. When I joined, I had to go through a programming course on the 650, the 7070, the 1620, the 709. I did the lot. And it was all rather expensive. And then we had a huge explosion then of programming languages and operating systems. And for the 790 alone, we had gone up to IPSYS version 13 by the time we were talking about the 360. I mean, we've gone through other things. There was a 4-track monitor system. There was a system called SOS, which was a total disaster, which was designed in conjunction with our customers. Essentially, the Share was a customer group. They did the design, we funded it, supported it, made it happen. The Share operating system was the example of what you get if you listen to your customers. Absolute rubbish. You have to understand what your customers want. And that's important. You have to really understand your customers. But your customers are not going to tell you what to build. They don't know. It's important to understand your customers, but you have to understand what they want. That is the key thing.
You have to remember, Fortran was designed by Share members.
No, it wasn't.
No, it wasn't.
Absolutely not true.
They had a hell of input to it.
No.
Not the lead, not at the beginning.
Not at the beginning. The initial Fortran group were entirely internal IBM people, 7 of them. Did it by themselves. John Backus' Fortran 1 was a brilliant piece of work by a very, very small group. And entirely with an IBM. And yes, Share had things to do with afterwards, but the initial design, Fortran 1 was a most remarkable system because its optimization was better than anything that came after it. It's really good.
I see it correctly.
So, anyway, we had all these operating systems, and languages were the current thing. In the 60s, everybody thought if you had the right programming language, you could do anything. All that we had to do was to find the right programming language. My view of what happened was that group staff, and a chap called Don Spaulding in particular, had decided we had to do something about the proliferation. And therefore they set up a committee. Or they set them up. And the terms of reference were something like this.
I've got that.
Well, I've got a tiny extract on it. What the terms of reference was a complete plan. What we want is a complete plan for the total system, for the total product range. IBM, World Trade, scientific, commercial, all the rest. What it actually said was in quotes. But what there was a strong pressure to do was the bit which is not in quotes, which is to make a compatible family of machines. I mean, no one knew it could really be done, but Bob Evans in particular was the president of the DSD, the development division, the large systems development division, had been involved in the 770, which is a mixed commercial scientific machine, had strong feelings about compatibility, and generally felt that it was going to be possible. But we had the spread committee, which John is going to talk about, and their commission really was to provide one truly compatible family of systems, scientific, commercial, and small, medium, large, US and world trade, which was a hell of a challenge. And they nobly went out and did it, and came back with a required conclusion. And they presented us with a marketing plan. Now, the original plan caused me personally a lot of worry for a long time. It envisaged a staggered announcement of machines, the first of which was going to be a small binary version of the Model 40, which is the machine being developed in Arizona. And immediately, there was a problem. What we were aiming at in the long term was going to be a grand strategy. But what we were allowing to work out instead of a grand strategy was one little small binary machine, which was an interesting machine, but not enough on its own to get anybody excited.
Could you just say something about what the market projections were? You say growth target, but what was the target? What kind of targets are talking about?
We were talking about 20% revenue growth.
Really?
The way IBM planned in those days was to draw revenue like that, straight line up, and then have its existing products and say, these will produce that much revenue because they're going to fall off in time, and these will do that. And what was left was the wedge, so-called wedge, and what you did was fill that up. That was the way planning was done. We just assumed that growth was a given. And the other problem, of course, was compatibility. The spread report said, well, yes, there is a sort of problem with compatibility, but what we've really got to do is to sell new applications, and people are going to be moving from tape to disk, and of course there is some new exciting teleprocessing applications to come, so what we're going to do is to ignore compatibility, and you're going to sell the new thing. Well, that's difficult, because even people doing new exciting things tend to have done some boring things first, which they like to do on the same machine and carry on all the rest of it. So compatibility was a big worry. And we went for about 18 months sitting on this plan, which was not a happy plan. And various people raising questions deeply about how we were actually going to achieve the plan. But IBM doesn't change, it was plans and it changes them. but it doesn't change them easily. A lot of pressure has to be built up to change a plan. And the catalyst in this case was the Honeywell 200, with its cheekily named Liberator program, which would take a 1401 program and run it on a Honeywell 200 faster and more cheaply than it ran on a 1401, which is a beautiful thing to sell. And of course it sold in large numbers very, very quickly, around about the end of '63. And then a very typical IBM thing happened. Tom Watson got involved and said, look, you're screwing around here. What I want is a solution in 90 days to the Honeywell 200. And suddenly we discovered something we knew already. The way to solve the migration problem was through emulation. We had microprogramming, we had the technology to do it. We had just never somehow exercised our minds to the point of saying emulation was an important thing. And it became important quite late in the day. But it was something marketing people knew they had to have. And the other thing was, look, let's not mess around announcing tiny bits at a time. Let's announce the whole lot. And then we can really announce the strategy rather than individual machines. Because the idea of announcing an individual machine was almost impossible. So that was changed. And quite suddenly, we had the Big Bang. It was the end of '63 when we really started making the assumption that everything would be announced on April the 7th, '64, which it was. 6 models of CPU, a complete range of new I/O devices. And the remarkable thing was that you could attach any I/O device to any CPU. You know, they weren't handcrafted the way they were before. And emulators for pretty well everything that was important. So suddenly we had a completely new, exciting thing to sell, which we sold with an enormous full text advert. You believe people don't read text. We had a full newspaper side of detailed text about the 360 series on the day it was announced. And of course we had people up to personally to show them around and all the rest. But it really made an exciting launch. But it wasn't quite the thing that or it wasn't done in the way that the Share Committee planned in the first place. Sorry, the Spread Committee planned in the first place. So that gets me to the end of the first bit. Where's Chris?
Yeah.
When would you like to stop, Chris?
I think you've got about another 10 to 15 minutes.
Okay, well, we'll do this a bit quicker. Programming always gets a short end of the stick. The reason I asked the question was I don't know how much you wanted to take into account in the later stuff.
Yes, well, that takes a little bit, yes.
So what we're going to talk about briefly is first the operating system, which is the innermost layer. And the first 2 charts are really about the operating system, the stages we delivered it in. Then the next layer on that, really, is what you have operating systems for, and really to get the files. I mean, that's one of the most important things I do. So the next layer up, look at the access methods, or what we used to call higher output control systems in those days. Then there were the languages. And actually, the most useful thing we delivered for customers, after all, was not just an operating system or an access method or whatever. We actually provided them with an environment in which they could write transaction processing systems, or a transaction processing system, with a way of writing programs that looked like ordinary batch programs but actually run from a terminal, which was CICS and IMS. So those are the ways I'm going to go through. If ever you hear anybody from ICL talking about how good ICL is, actually it's stayed remarkably constant. There's still the central idea of what we call a task control block, which people nowadays call a process control block or something, from which all the resources were hung. So the big problem with JCL was, or with the whole operating system really, was we were determined to avoid deadlock. And the only way we could see a big like or DOS or whatever. So that was the operating system benchmark. Of course, we couldn't do it all at once. We probably promised it all at once, but we couldn't do it. And so we had what I think we call a phased delivery. The PCP was the thing that was carrying a fixed number of tasks, 67, which is quite a bit later. Then the thing that was really the cornerstone of the rest of the 360 was MBT, multi-programming with a variable number of tasks. We got bounced into time sharing because General Electric had got the MIT contract because they had a time sharing system. We didn't have a time sharing system. So we said, or rather the corporation said, we better have a time sharing system, go and make one. So we made the Model 67, which is a special piece of hardware, a new time sharing system called TSS, which cost us a lot of money, and we didn't actually perpetuate. But it was our reaction to General Electric being better at the time. Eventually, we got onto time sharing option TSO, which was time sharing on the 360 using the basic operating system. And then, of course, not in this history, but later on came the next generation, where we had real virtual memory, virtual memory, and paging and all the rest of it. But that was later. But we got there, and it took us about 69 to get there. But we managed to deliver something the customers could use pretty well all the time. We did have some painful episodes, and I can remember Tom Watson standing up at Share and explaining that he was sorry. We got it wrong. He apologized, and the audience really accepted what he said. I mean, we were remarkably good at keeping our customers with us. I often go, or have been, to presentations where other companies' customers talk about their systems, and they bitch about their suppliers. I don't know why, but they're probably no worse than we are, but somehow we always manage to keep our customers friendly. So when they stand up and talk about IMS or whatever, we know what dreadful problems they've had getting their system working at the stage it is, but they always stand up and say what a good job it does. It's sort of strange. But anyway, in spite of all the trouble with the operating system, we kept our customer base, we kept our customers happy, and we delivered in the end. What machines are really for is to get the data. To get the data, you have to have some access methods, and we have a whole variety of access methods for disk and tapes, especially the index sequential access method, which meant you could run through a disk file sequentially, but it was indexed. So if you had a very sparse update of a very large customer file, that's a typical thing. You had a few updates on a very large file, you could do it without having to read every record. Made an enormous difference. So a job that you might match up for a whole week before it was worth doing could be done daily because you could skip over the records. I mean, it seems obvious now, but it wasn't at the time. Lots of people were still running tape systems way into the 80s. With a disk system, you could do anything you did with the tape system and do it faster. With index sequential access methods. We also had direct access where you had really numbered slots. VSAT was a sequential access method. Communications, we really fouled up. We assumed that people would like terminals or incoming communication data streams to look really simple. So the thing we meant people to use was QTAM, which took messages, put them in a queue, which happened to be on disk, unfortunately. So they stayed there for a little bit. Then they were popped off, and they were processed by message processing programs. The answer was put on a queue and eventually dispatched down a telecommunication line, which was absolutely fine, unless you wanted an instant response to a query. Because with the queuing stages in between, it just didn't work that way. So that was not good for transaction processing. The other one we had was the basic telecommunications access method, which was absolutely fine. But the problem was that because the operating system didn't treat communication lines indirectly, your program had to know a great deal about the actual physical unit and device address, the frequency that you're going to pull, all sorts of detail in order for you to write a terminal program. So that wasn't very good either. In the UK, they had a special one, whose name I now forget. That's right. Skipping a bit, the other thing was languages. Now the share committee, the spread committee had a word about languages. We decided since we had a range of machines that went across scientific and commercial, we should have a programming language that did the lot, which we called the new programming language, which quickly became NPL. Then we got some calls from some people who already thought they were called NPL. And we had to change it, it became PL1. And it was common language. It was specified by a committee. You often hear about the share role, but guys were also involved. We had two main customer groups, a scientific group and a commercial group, would you believe? The scientific group were called Share, they had 790s and things like that. The commercial group were called Guy, and they had 1410s, things like that. And we got people from both of these, and 3 people from IBM, and we specified a brand new language. We, of course, had no idea, really, about what specifying a brand new language was going to be like. And then, of course, we have all the other ones. And there's a big question about, were we really going to try and make PL1 the universal language? And the answer was, we hoped we could, but of course we did. And the very last thing is, the real answer came not from the people who were given the job. The real answer, and one of the strengths of IBM was that these solutions could bubble up from anywhere in the corporation. You weren't necessarily shut up if you had something sensible to say, whatever your place was. And there was one person in the utilities group, I'm going to talk about CICS first, because that's my favorite. In the utilities group in Chicago, who decided that what we really needed was a way of making interactive queries on large existing files. Now, the utility company had very quickly gone to computers because it was such a beautiful way of generating bills, which was a big job. And so they had these enormous files, long sequential tape files. If anybody wanted to query them, the only way you could query them was by actually running the queries against the whole file, which was obviously rather slow and didn't happen very often. So they needed some way of accessing existing files. So the files were put on disk, and they thought they'd solved the problem. But of course they hadn't solved the problem, because no one really had an easy way of writing programs to get these files on the disk. So we needed something to help them do that. And CICS was the system which gave you terminal access to existing data sets. And its emphasis on doing this efficient inquiry services. And also, that was done in Chicago. In California, in conjunction with North American Aviation, the big people were working on complex data structures for manufacturing, bills of material mainly. And they had the idea that the whole world was a tree, and all you had to do was get everybody organized in a tree, and that was the way the data had to be represented. The problem was, of course, you couldn't take your existing files, you had to migrate everything to these new IMS files. But once you did, they got enormous integrity, and they looked after them very carefully for you, and you could have a very strong, reliable system. But the difference between IMS and KICS was, in KICS you could use their existing files, in IMS you had to believe in trees. And they both were announced, they both exist. There was another system which was announced, which was the official system, which is now in complete oblivion. If anybody's heard of the Generalized Information System, GIS, no one here. That was the official one, and it just got announced and quietly died away. So, again, one of the strengths of IBM was we took a risk when we needed it done. We made some mistakes, but we listened to people at low levels in the company who told us we'd made a mistake, and finally sorted it out. And I think that readiness to listen was one of the characteristics of IBM at the time. We could really take things from a low level. The management at a very senior level had the determination to make things happen, but they had the self-confidence to listen to people who were criticizing them. And that was a very, very remarkable attribute of IBM at the time. And of course we had the power. We had a lot of money, we had a lot of resource, a lot of technology. We were in a very, very strong position. Someday you're going to have the story of how we found it all out. Anyway. Thank you, Chris. That's as far as I want to go. Thank you.
we'll have questions a little later on, perhaps if we have time just before lunch, but failing that, we do have a summarising session, questions right at the end of the afternoon. Now I'd like to call on someone who actually must take some responsibility for all of this. He was there at the time, John Fairclough. I'm not saying that all the other speakers, of course, they were there, but John did play an unusual role in the sense that he, having started his career at Ferranti, had joined IBM fairly early on and had worked initially at the Poughkeepsie lab for a short while, had returned to Hursley and worked on the SCAMP computer, which, as you mentioned in passing, but had then been brought back to be a member of the spread committee, which actually looked into the specification of what was to become the 360. So he has a unique role, and we're very happy to have him talk about it today. John.
Thank you. Thank you, Chris.
This is the first time I've had the opportunity to look backwards, actually. I've resisted the temptation to look backwards for many years. And the invitation to come and participate in this event was something that I found the temptation was too good to resist. Let me take you back. I agree with most of what Peter said, not all. The point, I think, that will emerge in my presentation, which differs in perspective from Peter's introduction, was that the driving force for a compatible family of machines was the programming dimension, and what was beginning to look like an enormous investment on the part of our customers and on the part of IBM. And the desire, the commitment to attempt a compatible family machine was really driven not by engineering bigotry, but by the desire to have a series of machines that could be optimally programmed to conserve resources, ours and our customers. And I think that's a slightly different perspective. I didn't mean to. What I have prepared for you, in fact, is an exact reproduction of the presentation at the end of this spread report that went to the IBM management. And I actually hope to have two projectors so that I could turn a replica of the presentation that was given to IBM management as well as my commentary on it. So with one projector, I'm going to have to multiplex a little bit, and you'll forgive me for that. Let me start one or two comments on the spread task force. Spread, Peter described, spread was put together in order to build this grand plan. The acronym SPREAD stood officially for Systems Planning, Research and Development, but more properly to Spaulding's plan to recognize or reorganize, I can't remember which, each and all and the anarchy reign. There were, if you like, individual business units given considerable freedom to operate in their, what was described as their self-contained markets, and of course they weren't self-contained markets, and considerable overlap and duplication was beginning to emerge. We in Hursley had spent the 2 years prior to this spread committee designing this scientific computer and modular processor, SCAMP. It was also the name of a girly magazine, I remember at the time. You remember that? And we were very proud of this machine. It was the first IBM machine to embody, probably the first real machine to embody Wilkes' invention of microprogramming with properly engineered read-only memory. You'll see examples of that in some artifacts later. And we were very proud of that machine, and along came IBM with the realization this anarchy was getting out in the other locations, and all shelved in favour of this grand plan. The task force sat for 90 days in a hotel that looked rather posh at the time, but it's now a cesspit. It's the New England Motel. It's on the New England Thruway just off it, and it really was elegant at the time, but it really has gone downhill of late. We finalised the report in December '61. I was invited, by the way, to join this task force primarily because I was so pissed off with the termination of SCAMP that I was threatening to leave, and the prize was come and join us in this task force. I was asked to go, and 10 days later, my wife and family were on a plane, and my house was rented. IBM, and still stands for I've been moved. We made a presentation which you're about to see in January 1992. Peter discussed the objectives. They're pretty. The members of the task force, names you may know, got together in this motel and began talking to each other. Intellectually, in terms of the detailed engineering, I did prepare an organizational glossary which I'll just flash up so you can see the charts I've reproduced. The copies that went to the IBM management include some acronyms and just to give you a feel for where the roles they play. There were systems under development too that you'll see mentioned. The 14LC was a low-cost 1401, and the 7030 top end of the line. The 1410X was a souped-up 1410, and the L2C was thought of as a small entry machine that would come in below the 1401. In fact, it ended up being a Model 20. Now, let me then start. These now then are the copies of the presentation. I'll make some comments on them. And I flashed these up rather quickly. The task force didn't set out to produce a design. On processor characteristics, that's all the management were told. Generally, IBM senior management in this era had been brought up in the punch card days. They weren't particularly knowledgeable about computer architecture, and so the presentation was a bit short of technical content, shall we say. Compatibility, formats, operations. Let me elaborate on that. These are points that are included in the report, written report, but not in the presentation. Each the program And then my major contribution to the debate. CPU coupling, standard interface. So that gives you a feel that that's not a comprehensive list of the engineering ground rules, but it highlights the key points that were in the report. So let me now then take you through the rest of the presentation, corporate presentation. I've used American spelling throughout. It's an accurate reproduction. So emphasizes ZE. New app on a more efficient way of producing our own application software, and as well as system software. Marketing. Announcements, you would then be able to declare that you've got the strategy to have a compatible family. I would say that dribbling out, you put all this money in, we'll announce all of these machines at once, and the following will result. We weren't sufficiently confident to say that. I think we needed more time to get design detailed and finalized. So, that was important. We then made a number of comments on how all of this could be made to happen. I described a number of business units all developing their own computing. Satisfying their own computing requirements. So there's a need to pull this all together managerially. All the 5 processes, right? Now we come to some of the technical characteristics. Corporate memory group shall. Cycle times to half a microsecond. Seems like forever today. That was the fastest core memory that was envisaged with those capacities. But with demanding targets on costs, a tenth to a half. Whatever they were costing at that time. Internal memories, ROM, for read-only memory, and you're going to hear more about that later. Cycle time a quarter to a tenth of the main memory. And as Peter described, IBM had a richness of technological capability, and all of that could be marshaled to support this effort. So it was a casters up, brand new design, casters up, brand new everything really. Every piece of technology was devised specifically to serve this family. And so an important part of this report was to marshal those technological resources at IBM and give them some objectives. Binary addressed files. The RAMAC was not binary addressable. And the number of subsequent files, disk files, were not binary addressable. suggested to take group as a second study. But then, to give the staff, the myriads of staff members there were in the corporate office and the divisional offices, give them something to do, and we devised a scheme so that we could begin to measure the progress of this overall effort. The flavour that compatibility was such a valuable contribution. I think anybody around. Introduction planning.
LC was the 1440, is that correct?
That's correct. Going back to John. So, Christopher, let's move on.
Thank you, John, for an absorbing presentation there. You'll be pleased to know that John is with us through the day and will be summing up at the end, so there will be a chance to talk further and raise some questions for those who have them, which I expect there no doubt be. Our next speaker is Ivor Jones. He will talk about the architecture and microprogramming from 360. He read mathematics at Cambridge, worked on EDSAC. He joined IBM Seminar in 1959 and worked on the 360 architecture and microcode. And he's ready now to tell us more about it. Thank you, John.
Nobody's mentioned yet, but architecture was one of the words that came in with 360. The idea that you could specify a machine, I suppose now we might say a programming model, which was invariant. It didn't matter whether it was made of transistors or valves or had magnetic core store or semiconductor. But architecture was one of Fred Brooks's contributions to the industry, to the computer science. Just a look at some of the technical. It drove the printer very well. It drove the card reader very well, but it wasn't a very fast machine. And these commercial machines had, and so on. It was also true that the large machines used were mostly driven by tape, and they used smaller machines to handle card I/O. In Hersley, not when we. And I don't think I ever saw the spread committee charts, and we certainly, some of those things came through, but as John said, we were a very secure company. And there's at least, I noticed at least one thing that we didn't do. But the hardware became people started believing in the machine, they didn't duplicate their runs, they trusted the machine, and therefore if it did make a mistake, they were going to be much, much more upset. So we had to have checking to discover to make sure that everything was right as it went through. As John said, we had a lot of argument about, the next point, two's complement. Most of the IBM we had a fair amount of argument about that, and I think we had to do a bit of educating to prove word boundaries. That's to say that we came up with a whole lot of terminology, bytes for characters, half words for 16-bit quantities, etc. Words for 32 bits and double words for that. And these were the formats that came out. Half-word quantities had to be on these boundaries. Fixed point and floating point had to be on word or half-word address boundaries. That sort of the character data and the decimal data could be on any address. I don't know whether we did it because the Sprague Committee said it, or because we didn't have too much argument about binary addressing. We came down to addressing bytes, characters. It was clear we needed better than words, and although we addressed down to the decimal, 4-bit decimal unit. One of the ground rules we decided was that we would use.
Could you differentiate the Hersley influence and the rest of the corporation? Was this largely Hersley?
No. I think it was all discussion. I might say the way we worked. I went over in 1961 for I think it was a 2-week business trip, which lasted 6 weeks. At the time, we addressing scheme we came to was the base addressing. We had to quite a large slice of market for our machine. So balancing the size of the address versus the space within the instructions, we came down to base addressing, a 12-bit offset, which would cover most data structures, but on the other hand, there was a base register which would from which that offset was measured, and we would use full-length registers for these base registers, and we could manipulate them with the full fixed-point arithmetic and logic instruction and so on. And I've summarized a great deal on here, but and so it made up sets of instructions in formats that were based on a 2-byte half-word, 1, 2, and 3 half-word instructions. I talked about several of the instruction formats, well, the types of instructions, the SS, decimal, and logical character operations. The RR and RX were the register instructions. Some of the more interesting operations are ones in the middle, the storage immediate, where we could put an 8-bit character, just use immediate for inserting in storage or comparing or masking, things like that. one of the most useful instructions there was load and store multiple, which was quite useful. Branching and sequencing generally, and when you looked at the definition of the instruction, you found out exactly what was going to happen. There were also some more specialized instructions for counting, this count and branch, or and there was otherwise a program that was could not be inadvertently or deliberately sabotaged. So in order to get into the supervisor, we had a tremendous number of classes of program exceptions, things that the way programs could go wrong, and for example, storage protection. We were careful to close off all the unused opcodes so that later implementers didn't have to go through this discovery process. Invalid addresses, I'm sure a lot of the code was just checking have they used an odd address when this is a fixed word operand, etc. And slightly more useful things like overflow detection, those were all classed as programming exceptions. Supervisor call was an instruction to get into the supervisor, but again, you could pass it on. External interrupts. External interrupts, I think, were possibly usable for what do they call it? They were certainly going to be used in the multi-system feature for the machines to tap each other on the shoulder for various purposes. I'm keeping clear. The key thing in the interrupt system was the program status word, which was a double word unit. But what was were the I/O channels enabled to interrupt or not? What sort of protection keys were all to be set up by the control program? And there was also room in this to put in some sort of interrupt code which would explain that it was a protection check or whatever. There's one other point there that since we had gone for variable length instructions, and this instruction address was you needed this instruction length code to tell you how many syllables to go back to the cause of all the trouble. And I mentioned some of the requirement instructions for those VSW change all of that. And we came up with a scheme for that. We had an interval timer which was positioned in memory, and this in fact created one of the external interrupts. And lastly, the wait state. We would put the machine into a wait state where it was not using memory cycles. It could sit and allow I/O to carry on, and then it would crank into operation when an interrupt came along. So we have a sort of conceptual machine with channels which we'll hear about later, with registers. A lot of memory, and I mentioned the key store and the timer. And then the switch to the microprogramming subject. There were 5 teams of engineers trying to implement it. And in the SCAMP machine, and very well.
We invented them on SCAMP in a last-ditch attempt to persuade everybody that we could emulate the 7040, 7080.
the typical control system looked like this. If we start at the read-only store at the top, a micro instruction would come out into the data register. In Wilkes's scheme, those outputs, they didn't come from a store with words. They were cores, but and if you wanted a control signal, you put a wire through the core. But we developed into the scheme with a word and ones and zeros coming out, and instead of taking signals directly to control data path, we went into decoders, which were a lot more efficient. You can see this late register. Some of the signals had to be used early in the cycle, some later, and therefore you needed extra registers. Some of the gates would relate to the finding the next ROS address, and some of the decisions as to where we go in the read-only memory would depend on bits in the data flow. In the case of the Model 40, we built, looks a bit complicated, but in fact it was a machine with 4 registers, which were essentially 2-byte registers, 4 2-byte registers, and the main memory is here, and we have a local store. And the main memory turned out at 2.5 microseconds in the end. The cycle time of the machine ended up with 625 nanoseconds. This local store, you could read it or write it in one cycle, but not read over. And so we had various parts of data flow. The adder we had was a 1-byte adder, and we used 16 bits to specify one input to the adder, the second input to the adder, what function the adder would use, and how we would set the carry, whether we wanted a 4-bit shift, and then finally we had to direct the output back to one of the registers. And there were similar loops for, there were 16-bit data flow between the local store and the registers, and we could take something from one of the registers to this R register and then direct it to somewhere else. There was another sort of cycle here of registers which were addressing the local store, and we had about 5 bits to describe the combinations of which one to use and whether to increment it as we went through. Some of the features of the Model 40, we used the local store, we used what we call an indirect function register, which I guess would be like an op register in a hardware machine, but it was a sort of late invention. And the strange thing was that a lot of these features, for example, the independent carry matches, we discovered quite independently that the other machines had got very, very similar features. We used the same data flow for I/O. I/O operations, the channels used that data flow for the complicated bits of starting and chaining operations, but they tended to have independent hardware for just pushing data in and out. And I think programming that machine was sort of all-in programming. We were very conscious of the number of words we had available in the read-only store, and saving them at all costs was very important. And one had to preserve a balance between making code as compact as you possibly can and making it impossible to change if you made a mistake. But there was a great deal of, I've got a piece of a logic page here, and there were a great number of things that one was doing. Take this one, for example. You can see that each line in that box, the second or the third line in the box with the star and arrows, that's an arithmetic statement for the ALU. Gosh, I can't remember half the things now. It's a long time ago. Here's this statement is talking about the 2-byte data code, putting something into the local store, and but one was trying to combine paths where possible to save on the words. This particular page is in fact to do with the instruction fetching, and I suspect that this local store is actually putting away the current value of the instruction counter. At any rate, this machine would have been a great failure. In Cambridge, we had a machine with a loudspeaker attached to one of the bits of the instruction counter, and you could always tell when the engineers were running the diagnostics and it was going to be ready for other people to use it, because the last diagnostic program had a particular ring to it. And in this machine, we put the instruction counter into a core memory, and that would not work. Now, in the 20 years following 360, it was extended, and additions were made. Notably, in about 1970, we came out with dynamic address translation, relocate, etc. that we mentioned. The instruction, the retractor maximum string length, and compare and swap was a more powerful form of semaphore type operation for synchronizing processes when you had multiple CPUs. And even later on, we came up with the XA architecture, which we're now around about 1980 with 31-bit addressing and some improvements in the number of I/O channels and the addressing speed there. So this chart, I think, shows some of the things that we left out, if you will, from the architecture.
I would say the vision we had in Stren was we would do well if this architecture lasted a decade.
Yes.
We really couldn't see it lasting more than a decade.
And I think that as well as the word architecture, the idea of hardware compatibility has become better standard. Checking is much more widely used, microprogramming, emulation, and the ideas of multi-programming, supervisor state, etc. The I/O interface was a tremendous success, I think. The program standards were condition code. Practically every machine is now based around 8-bit bytes, and the language of dumps is now hex and not octet. Thank you.
things, I didn't put it up. Would everybody please come back, if possible, and I think we really want to make a good start at about 10 past 2. 10 past 2 for the resumption. There is a cafeteria right outside here at the back, just behind me. You can certainly get something there. There is also, would you believe it, a snack bar called the Megabyte, which is on the first floor, where you can get, I think, just a coffee and a bun or something, not much more. For those, of course, who wish to be energetic, one could eat probably at South Kent, but I wouldn't advise it because we're really going to be sharp on our assumption at 10 past 2.
Shut the door behind you. I'm going to try and get a few minutes to eat. I pressed it, but I don't know. I pressed it this morning when I came in. I've got this one in there. My hands. No, I don't think do that. Well, if they come in and do that, I'll come in and do it. That's what you're doing. Yeah. You know, that's some fun. There's been
worn out. So.
Okay.
Right.
I wouldn't thought you guys.
No, that's all right.
Thanks anyway. So it's working then.
Yeah, it's back operating fully functioning.
When was this? When was it repaired? I mean, I didn't know. I was still pressing.
Yeah, the extract fan will still come on, so it's still full airflow.
Yeah.
All right.
But there's no heating.
No.
Because they complained about the cold.
Yeah, well, we set the temperature up yesterday. We did that yesterday. Yesterday afternoon, May 10th. So it's coming in at 25. Your air supply is 25 degrees.
Oh, well, thanks.
So that should be okay.
That should be okay.
Well, I'll check it again tomorrow morning first thing because we've got Roberts tomorrow.
Yes. Right, thank you.
Let me
I
just-
don't want to lock the doors or not now.
See? Right.
Yeah.
A very short second. If you feel that, that's your air coming in.
Yeah.
Should be more than
Yeah, that's fine.
that. Like that.
That's fine.
But you see, you've got your indicator lamp in there now. I've just got to get the slider.
Oh, I'm going to start it, I've still got an indicator.
Yeah. But the bloody maintenance people, Satchwell, they keep pulling their guy off site. Because I was expecting that to be done, finished, sorted, and away. But you know what it's like these days.
Yeah. Okay, thanks.
Alright.
Are you studying in this yet?
No, I'm going
I don't know where to look for or not. They're closed just after take pot that.
Yes, it's, I left for glasses, so I have to get back.
They'll be in and out, won't they? So there's no way I can lock up anyway.
Well, I think I probably will, yes.
I'll leave it.
With
I'm going
you
to try and
back.
get a bite to eat. Okay.
You back this up too.
piece of art that we can't see there.
Yes. Oh dear. What time is it?
10 past 2, Peter was suggesting. Yes. Fascinating order.
Well, I couldn't make it this morning. I had to come up. Well, I got here about 12:30, so not to interrupt.
Peter Titman gave a first overview of the challenges in those days, and then John Fairclough began to talk about the spread committee essentially. Are you working with IBM?
No, I wasn't. I started my computing career on 360s.
Yes,
So I know a lot of that. Well, I don't know a lot of them. I certainly have had a lot of dealings with them.
So-called Ida Jones has been talking about the architecture of microcoding essentially. Talk about the 140 anyway.
Yes.
Did you start with 140 or
Well, I started with 30.
Yes.
And I certainly went through the 40. 30, 40, 50, and 65, I think. 40 was very good.
Yeah, that's really explain what the job it was to maintain total compatibility, which is rejected from the situation was in 120 or something. Right up to the
Oh, yes,
90.
they did do it. 25.
The most successful 30 was sort of
Yes, the 130 I think was the best selling one. But there was a lower one. I can't remember what it was.
And later there was 25.
Right.
Actually, it's very difficult to get complete compatibility with the 90 instruction set and so on.
Yes.
On the 30, he was talking about had an emulator for the 1401. So anyway,
Yes.
that's what you had 1401.
That was before my
Super
time.
photo, etc.
But the firm I was with had migrated from a 1401 to the 30, and from time to time they used the emulation for switch.
Yes.
But they didn't leave it low.
Getting complete emulation was very difficult, especially if the customers were playing tricks with the 1401 outcomes, which you couldn't do, very hard to emulate those different machines.
I mean, the things you used to do to play around with those machines was amazing. Well, a lot of people here from IBM.
Quite a lot. You may see the attendance register on the sign it somewhere. And there's quite a lot of IBM. You recognise that they're still wearing the IBM people almost, and you know, black shirts, etc., black shoes. Yeah.
been round everyone as far as getting copies of what they say.
I've been round, but I haven't succeeded, is all I would say. I think that people are just speaking from their visual aids, I think.
I think I collect some charts. Some of them are definitely out of date. Right? But they may help.
Yes. Yes.
Especially when it comes to slides. The trouble is in the slides that John has got. Obviously they capture pictures. And indeed they don't capture all the text. But I do have, I think, fairly complete sets. But there are still.
I made some notes as well, which may have helped to him, but it's quite a lengthy job. Chappie does the transcription.
Oh, I see.
He's a member of the society.
We better give a guided tour.
You can get out from that.
But can you actually... Might be alarmed.
Should I make representations to Robert, or should I just ask him what we do? I mean, basically, we're going to... You're happy to live with it, or should we go first?
What about storage?
About form signing.
I think you see, half the time, we
They
don't
did
have
bother
time
to
to
go out.
really actually do it. Every place they say, look, I'm funding it, so there's those radio shows, because they're moving premises. So what do you do? I haven't got time for the organisation. This is one job, so would you sign it now?
Presumably the quickest turnaround is going to be 3 days. It's going to get there in 1 day, it's going to be signed. Well, the quickest turnaround could come back in a day for signature. The longest could be 3 days. So I think what we need to do is we need to play along with it. Except we need the power to say that in situations where it can't be delayed, we have power to go ahead. So we have strictly power to proceed. But then what about transport?
Well, that's it. So I'll put it through them. And
I'll speak to Robert.
we could put it in the Pegasus room as a neutral. So, then,
We collect, not through Brian.
yeah, but still have to put the guys where we go.
Save you an object.
Well, no, that's all one of
Puts another tier of nonsense. Yeah. I'm just waiting here to see Joe Towler too.
I came down at 1 o'clock, they were still becoming.
Yes, or maybe it's due to quite fast then.
Possibly. That's the danger.
They've really strapped it up. I mean, hopefully it'll last longer you to go on with for a while.
So she knows what's going on. That's actually mind you, that's how she said it, but I should imagine, I mean, saying that he'd give me a date when he was coming over, but I've not heard anything. I've been chasing him. He was offered to put it in the I know it's keen time or help. Yeah, he said he was going to see it himself. Nice to meet you. The thing that attracted him was photographs still in the aviation an early area tied to a tree at farm test